except that I cannot share while you're sharing, Naomi.
Okay, okay, that makes sense. How do I unshare?
Click the red that says stop sharing.
Do I have it? Yes, I do. It was buried. Okay, go ahead and share.
Got it. Let me. Okay, I want to welcome everyone to the fourth in the series of ACS Physical Chemistry Division virtual seminars. And I'm Ann McCoy. I'm the past chair of the Phys division. And we have with us Rodrigo Noriega, Carlos Baez, and Christy Landis. And Christy is our vice chair-elect, I believe, of the division, or maybe vice chair at this stage, and will be program chair for the division next year. Just a few words before we get started with today's seminar. I first of all just want to again thank Phys, who has provided sponsorship for us and has basically made it available to us, this Zoom channel, which has been huge for us. We've got a couple of upcoming seminars. Naomi Halas will be today, as you guys all know. 4 weeks from today is Phil Geisler from Berkeley. And then Jerry Richmond will be in late April. And I encourage everyone to sign up for these. I'd also encourage everyone to sign up and register for the ACS meeting, which is the first 2 full weeks of April. The registration is actually very reasonable this time around, and it looks like it should be a very exciting meeting. And so with that, I will stop sharing screen and turn this over to Christy.
And I will not take too much of Naomi's time from her talk. It's my job to introduce our guest speaker today, Professor Naomi Halas from Rice University. She's the Stanley Moore Professor in Electrical and Computer Engineering, but she also has appointments in Department of Chemistry and Biomedical Engineering and Physics and Astronomy. And the reason that she has appointments in all those places is that her research really exemplifies, kind of what modern physical chemistry can be if you want to take things really from basic science all the way to the implementation of new devices and even products. And for that reason, she has, just tons and tons of awards. But I think the thing that exemplifies that she is a scientist as well as an engineer and an entrepreneur is that she is a National Academy of Science Fellow. She's a National Academy of Engineering Fellow, and also in the National Academy of Inventors, because she's just an example of someone who's taken, from the beginning of her career, basic discoveries and nanoscience in particular, and then taken those all the way to devices, and then now to products that are being used and marketed on consumers and also patients. And so we're very honored to have you join us today, Naomi. I'm not going to take you. You've won too many awards for me to mention all of them, but those 3 things to me exemplify what you are in terms of inspiration. So thank you for doing this. And for so far as the people listening, for those of you who haven't joined us before, we'd like you to put your questions in the chat feature, and then we're going to curate those at the end. I'll put instructions in the chat so that you all have them. But Naomi, take it away.
Thank you very much. Thank you very much, Christy. That was very kind of you. Okay, very good. I'm moving into the share screen aspect of what we're doing. And I'm also, okay. So if I move a little, very good. Okay, so I think that we have, let me move this off screen. Very good. Okay, so my original title was a little bit broader, but I realized this is a shorter kind of webinar. I wanted to make this more focused on one subset of the work that we do. First of all, I want to thank everybody for attending today, and I particularly want to talk to the students. I'm so thrilled that we have a combination of faculty and students who are tuned into this. And the one topic that I'm really excited about in our work, because I think this is really an opportunity to fundamentally change the way we think about and the way we run chemical reactions, is light localized chemistry with nanoscale antenna reactors. And I'm going to explain to you what all those words mean. In particular, what is an antenna reactor and how does light localized chemistry? Because familiar with certain aspects of photochemistry. We know about photocatalysts of the molecular sense, but this is very different. The mechanisms are different, and what you can do with the kind of antenna reactor nanoparticles that I'll talk about today are fundamentally different than what has been done before. And I will hope to explain a little bit about this. So this is work that we've been doing over more than the past 5 years, largely funded by the Air Force Office of Scientific Research. And much of this work has been spun out into the work has been licensed. The patents have been licensed by a company that is thriving and growing called Syzygy Plasmonics. And you'll hear a little bit about their strategy at the end of things. Now, I'm not sure that I can move anything forward. Okay, why does my screen not move forward? Okay, no.
Try clicking on your PowerPoint slide and then hit forward. Sometimes it defaults that it thinks you're on Zoom.
Okay, I will do that. They're very good. Okay, so the starting point for my talk, and the starting point for my talks for the last many years, more than 20 years, I'm sorry to say, or I'm happy to say actually, is are noble metal nanoparticles or metallic nanoparticles that interact strongly with light. And we always, great example of that are gold nanoparticles and silver nanoparticles. And in every textbook or every talk that you hear about this, you see the Lycurgus cup from the British Museum, and you see very often this is a stained glass window from Chartres. So the beautiful the beautiful optical properties that we associate with these structures from antiquity or from the Middle Ages have to do with the optical properties of metallic nanoparticles. Even though when these materials were made at the time, they had no idea. But modern science has brought us, in the last, really since starting with Faraday onward, has brought us to a modern knowledge of metallic nanoparticles, in particular those with, so we can often, so the generic ones that we think of course, are the coinage metals and noble metals. So we will sort of continue with that. So the example that where I think the modern science starts is with Faraday. And Faraday is, so one of the things that he did, he was a great public speaker, and he figured out how to make gold nanoparticles. And so the nanoparticles he made, he would bring them in a little vial on his public lectures. But these nanoparticles are still stable, and they're in existence. They're in the British Museum. So that's a photograph at the very bottom of a beaker where literally Michael Faraday's colloid is still stable and still visible at this institution. And Faraday is, of course, important for a couple of reasons. In electrical engineering and in physics, Faraday is an extraordinarily large name in terms of electricity, but he's equally large in chemistry in terms of being the father of electrochemistry. So his understanding, eclipses both chemistry and our modern understanding of light. So he's, of course, a very good starting point. And so how can we think of metallic nanoparticles as in the gold nanoparticles that Faraday that Faraday first demonstrated? We can think of this of a sphere of basically delocalized electrons, much smaller than a wavelength of light, as a sphere as electrons that have a well-defined resonance. So they act as if they are an incompressible fluid. The electric field pushes on them and they push back. And so they act like a little harmonic oscillator. And like a harmonic oscillator, they have distinct resonant frequencies. So if you're in gold, you have one frequency. If you're in another metal, you'll have other frequencies. They have to do with the electron density, but then also this is determined by shape. So this is a calculation of a light wave incident on it turns out, aluminum nanoparticle off resonance. The light wave passes right by, but when the light wave is, I still have to figure out how to advance my, okay, very good. But on resonance, the light wave is affected very, very strongly and interacts very strongly by the presence of the aluminum nanoparticle. So in other words, the nanoparticle itself has a cross-section much larger than the physical cross-section of the nanoparticle, and it bends the light waves around around the nanoparticle. So this has many meanings. So unlike exciting a molecule where you have one photon in, one photon out, for example, for a luminescent molecule, here you can have many, you can couple in many photons at the same time and have effects relating to nonlinearities. And that is actually important to us. So I'll say more about what happens when light interacts with a nanoparticle in a moment. But I also want to mention, oh my gosh, okay. I also want to mention, now I'm figuring out how to advance my view graph. So for a sphere, we have one resonance. This is just an example of gold. I'm sure many of you are familiar with the properties of gold nanoparticles and their well-defined plasmon resonance. And we stretch a nanosphere into a nanorod. Because we've broken symmetry, now we have geometrically, we have created two resonances, a longitudinal resonance and a transverse resonance at two different energies. So the shape of a nanoparticle can also control the plasmon resonance energy. This energy is very important when it comes to chemistry, and we'll be talking more about the energy of that plasmon resonance. So what I mean by the energy is the photon energy that corresponds to the wavelength of light that excites the nanoparticle. And we'll see more examples of that. And you can get very complex in terms of understanding not just a single nanoparticle, but if you bring two particles together or make complex shapes, then you have plasmons on each individual particle, and they will mix and combine just the way wave functions do in very simple quantum systems. Just like a diatomic molecule, you have molecular orbitals instead of atomic orbitals that you have for the individual atoms. When you have two plasmons interacting on a single structure or on adjacent structures, then you can have you can have plasmons now at completely distinct energies related to the more complex structure. For example, you can have what we call bonding and anti-bonding plasmons only because they resemble molecular orbitals if we have two particles adjacent to each other. So this is a well-defined, a very well-known phenomenon in plasmonic nanochemistry and in plasmonics in general. And it stretches to more complex structures like hollow spheres, for example, and we can go on and on about different types of structures and how the geometry then controls the type of resonance. There's a lot of really exciting physics related to that. We're not going to go to complex shapes today, but we'll talk more about specific applications. So before I get to the application that I really want to focus on, I want to just give an example. As Christy mentioned, there are many ways in which plasmonics is sort of moving forward in this. It's really been about almost 20 years since the name plasmonics was developed, and it really sort of became a field. And so it's interesting just to see where are areas that where there's very active and interesting research, and some of this has to do with the fundamentals. So one has to do with new materials. So we've had a lot of interest in, for example, going not using the coinage metals or noble metals, but actually looking at earth abundant metals, in particular aluminum. And here the chemistry is really unique to this type of metal. We're very, really fascinated by just how unique this is, but yet how we can still, connect with our understanding of FCC crystallography and understand the basic shapes that we can synthesize of nanocrystals using this type of metal and its unique chemistry. But then we can jump to applications, and one application, for example, is water treatment. When you shine light on nanoparticles, they can generate very strong photothermal effects. So you can induce phase change, and you can actually you can do things like disinfection, but also you can create steam, and you can do desalination, distillation type processes with sunlight and with solid state lighting. Another area that is very, very big that in the area of plasmonics, and many of you might be familiar with this, are topics like surface enhanced spectroscopies and different types of sensing modalities. And sensing is an interesting, is always a huge needs for sensing. And what we've been looking at very recently is how we can use things like surface enhanced spectroscopies. That's certainly now a very well-known field, but how we can actually couple this type of modality to some new methods of analysis like machine learning to understand how we can very rapidly distinguish the components in complex spectra. How could we identify whole families of molecules that might be, for example, toxins in a water supply? One also, so I've been made a big point about metals, but actually this field and some of the physics behind it goes beyond metals to dielectrics now. So the whole there's a whole field that is just more recently emerged called metasurfaces that is based on some of the plasmonic properties of metals, but actually uses instead insulators. So materials like metal oxides, titanium dioxide, zinc oxide, and they can be used to develop some very, very interesting optical phenomena and optical properties. Historically, we were one of the very first groups. We were the first group, along with our colleague Jennifer West, to show that you can use nanoparticles. If you tune the plasmon to a wavelength that passes through tissue, you can use them to destroy tumor cells. And this work has really advanced. I'm not going to talk about this work at all. It's in the clinic. It is in some very successful trials on early stage prostate cancer that are being done across the US at this point. And so this is something that we feel is really great. We are so proud of this because it's really affecting lives very positively, saving lives, and also affecting the quality of life of patients with early stage cancers. The topic I'm going to talk about today is how we can actually do chemistry using plasmons on a metallic nanoparticle, an optical antenna, and how we can combine this optical antenna with little chemically active sites implanted on the antenna. And I'll show you some different variations of this geometry, but that's the basic idea is antenna, but then also as denoted by these sites, reactors, and in combination, how we can actually do how we can do various chemistry reactions. So why do I want to do this? So I like to give this example. So if we just look at energy, everyone is worried about energy because of climate change. You don't want to, any industry that expends a lot of energy, you really want to look at and say, do they need to be expending this much energy? And so the biggest bad boy in our industrial sector, and it's worldwide too, but these are numbers for the United States, is the bulk chemical industry. Oh my goodness, and I'm talking to a bunch of chemists. So the energy consumer, the biggest energy consumer of all these different industries is bulk chemistry. So it takes, as you know, if you want to do a chemical reaction, you heat it up or you apply pressure. Those are the conventional ways people have been running chemical reactions for the last 200 or more years. And this requires a lot of energy to get into the parameter space where you're actually where you're driving a reaction to the desired product. So not just in the reactivity, but then of course in separations, that also is a tremendously energy intensive area. So in general, it's really important for us to look at this as a huge challenge. Do we want this to be the major consumer of industrial energy, or are there smarter ways, not just improving incrementally on catalysts that exist, because that's very, very hard. The catalysts that exist now are catalysts that have been developed and refined for decades. So it's hard to make more than just little incremental improvements. So what are really new ways to drive chemical reactions? So the answer, not big surprise, if you're attending this talk, the answer has to do with plasmonic nanoparticles. So let's think for a minute about the properties of a plasmonic nanoparticle when we shine light on it and how that can actually tie into doing chemistry. So the first property that's very important that we can never forget about is when we shine light on a light of a resonant wavelength, right? The wavelength that will excite the electron cloud, a collective electronic resonance. So even a single photon would excite the entire electron cloud within, say, a 10,000 electron or 10,000 nanoparticle, for example. So we excite this coherent oscillation of electrons with an incident wave. And there can, of course, be light that is scattered, but also there is energy coupled into this nanoparticle. And the oscillation will be damped very rapidly by the vibrations within the nanoparticle, or known as phonons in the condensed matter vocabulary, and will lead to the carrier relaxation will then lead to thermalization. And so you can have very strong macroscopic temperature increases when you shine light on nanoparticles. So this is obviously increasing temperature is a very important way to drive chemistry. So there are several issues here. When you shine light, you have a very large polarization, and that it creates very large optical fields. You have within this context also hot carriers that are excited that then relax. And then the thermalization of this provides the photothermal effect. So from left to right, you have these three processes that can all drive plasmonic processes, and they can also be involved in chemistry. So where things get interesting are if we look is particular at the idea of exciting carriers. So if I excite a plasmon, the plasmon is an oscillation of the electrons in the nanoparticle. That oscillation will decay by generating an electron hole pair. Let's just say hot electrons. We have a cold hole and a hot electron at the same energy as the incident light. So whatever photon energy corresponds to that wavelength of light, I will generate an electron hole pair with that equivalent energy, with E equals H nu, that equivalent energy. So I generate hot electrons and hot holes. So this non-equilibrium population is relatively short-lived, but it's long-lived enough that if I have a molecule sitting on the surface of that nanoparticle, then I can actually have charge transfer from, for example, the hot electron population. If we look over here, the hot electron population to an unoccupied molecular orbital just outside the surface. So the relationship between the electrons inside the metal and the adsorbate outside and its ability to interact with the substrate allows us to have, by, for example, tunneling processes, we can create hot electron processes, we can also create hot hole processes, and both of those can lead to a chemical transformation of that adsorbate molecule. So the basic theme is if I can make hot electrons, and these are hot electrons generated just by plasmon decay, then they can actually induce chemistry. So one particularly simple form, which I'll show you in a moment, is in the case where we have a hot electron that transfers to a LUMO level. All of a sudden, what used to be a neutral adsorbate can be now negatively charged. So we have what is called a transient negative ion sitting on the surface, and this can undergo, that lowers the barrier for a lot of different chemical transformations. That can undergo chemistry once we go from a neutral state to a negative ion state. So let's see an example of this. This is the first reaction we ever did in this context. So I like to refer to it as the simplest reaction that we can think of. It has no side reactions, where we have H2 molecules interacting just very, very weakly with the gold surface. These are small gold nanoparticles. We flow the H2 over the surface. We also flow D2 over the surface, okay? And what we want to do is we're going to dissociate the H2. Normally that's a high temperature process. It's a significant barrier, but we're going to do it at room temperature. And we're going to do this with light that is resonant with the actual plasmon. We're going to excite the plasmon of the nanoparticle. So as I said, we flow H2 over the surface. It associates only very, very weakly with the gold surface, just very, very weakly physisorbs. Then we turn on the light, we excite the plasmon in the gold nanoparticle, and that the hot electrons of that, as that plasmon decays, transfer to the LUMO level of the H2 molecule. So it becomes H2 minus. Okay, H2 minus, the barrier to dissociation of H2 minus is much, much lower than the barrier or dissociation of H2. And so we undergo dissociation. So it's less than electron volt actually barrier. And so how do we detect something like this? We detect this by doing a really simple experiment. We flow both H2 and D2. And if we ever measure HD when we have as a function of illumination, right? If the light is on and we detect HD, this is the only way we could make HD is through the generation of hot electrons by plasmon decay. And so this is what the actual experiment looks like, very small gold nanoparticles. And then we use a mass spec to detect HD. And then when the light is on, we see there's a little temperature increase, but that's not nearly enough to actually dissociate gold. So it's not a thermal process. It's just a few degrees. And then we turn the light off, it goes back down, and when the light is on, and so we see this clearly. Light-induced process. It's not a thermal effect. It is a purely hot electron effect. And so this got us very excited that we had this very clean experiment that showed that we can extract hot electrons, and we can do decomposition in a regime where people, here we are with basically, this is being done at room temperature and being done only with illumination. So that's very exciting. So at the same time we were working on this, we decided to also make aluminum nanoparticles. And aluminum nanoparticles, as I mentioned before, they have a really beautiful, unique chemistry. I'm not going to go into the details of the chemistry. That's a topic of a whole nother talk. But it's really fascinating because they're the only nanoparticle that we know of that requires a catalyst for their synthesis. But we developed a way to make aluminum nanoparticles of different sizes. And as you vary the size, you can vary the wavelength of light that's resonant with the nanoparticles. You can vary the resonant energy of the plasmon in the nanoparticle. As you make it larger and larger, you can lower the resonant energy. And so this is a TM image of the nanoparticle. So aluminum is a very reactive metal, as many of you know, and it is always terminated by a very thin oxide layer. And so this is actually what you're seeing in this TM image, is the oxide layer surrounding the otherwise crystalline nanoparticle. So we tried to do that same experiment that I showed you with gold. We tried to do the same experiment, basically dissociation of H2. We tried to do that with aluminum, and very much to our surprise, it worked very well. And why would it be surprising? Well, first of all, we don't have a clean aluminum surface. We have this thin layer of oxygen, this thin layer of oxide, excuse me, that terminates the aluminum nanoparticle. And but this layer is porous enough that it lets H2 through the layer, which is about you can see here about 2 nanometers, and is able to interact with the surface. So we're doing basically exactly the same chemistry, where we excite the nanoparticle and we generate hot electrons, and the hot electrons then transfer to make H2 minus, and then H2 minus dissociates. Now, what's is a little different about this is that it turns out the actual plasmon of the aluminum is not as important as the interband transition. So, of course, aluminum has a very different electronic structure than gold, and so it turns out that there is an interband transition down around 800 nanometers in wavelength, the incident wavelength, around 1.6 electron volts. Okay, which has to do with the fact that there is an unoccupied state above the Fermi energy for the aluminum. And so this is important for my argument later. But basically, this shows you the plasmon of the aluminum nanoparticle. But then when I see how does H2 dissociate, it doesn't dissociate the largest rate of dissociation is not at the plasmon, it's at this lower energy that corresponds to the interband transition, which is part of the material of the structure. So I'm sorry, I mentioned the unoccupied D band above the Fermi energy for aluminum, for those of you who know a lot about metals. So we found this to be very interesting, that we could do this dissociation reaction at all. But we also found that very interesting, this has more to do with the density of electrons within aluminum at this particular energy than it has to do with the plasmon. But I'll say more about that in a moment. Okay, so now what I'd like to do is talk about this from sort of the bigger picture. So as I just demonstrated, metals like gold, silver, aluminum, they have plasmons. And so they're very good optical antennas. They interact very strongly with light, but they really don't have a chemical handle, right? So they don't interact strongly with adsorbate molecules. So these plasmonic metals, so we'll throw in copper as well, which is also important. We'll mention that in a moment. So gold, silver, copper, aluminum, they're great antennas. They capture light, but they're really not good at interacting with adsorbate molecules. So if you talk to catalysis people, they'll say, oh, look at these, the transition metals. These are the ones that bind strongly to adsorbates. This is how you really want to do catalysis. So how could we possibly combine both of these ideas? And so we thought, well, we could do them in a relatively simple way. Here we have aluminum. We'll start with aluminum. It's a very good antenna. And so if we put small islands on the surface of aluminum that are reactive, then we can perhaps do experiment. We can kind of get the best of both worlds. We can have a catalytic handle, plus we can use the plasmon, which is essentially this cloud of electrons. We can use that to, for example, to transfer hot electrons and make a negative ion state. We can start to do some of the chemistry that we just began to see in those first couple experiments with gold and aluminum nanoparticles. But we can do more chemical reactions. We can use more types of adsorbates. So this could really open the door for different things. So the first reaction that we decided to do involved taking aluminum. There's an aluminum nanocrystal here, and putting small palladium islands on its surface. So here we have the aluminum is the antenna and palladium is the reactor. And so if we try to do the exact same experiment that I showed you a minute ago, just using the H2D2 experiment, and we try to do this with this island structure again, instead, what we find is that we have we see very strong, and this is actually not reflected directly in the data, but actually when we have an antenna reactor, we have about 50 times greater rate of H2 dissociation than we do when we have just pristine aluminum nanocrystals, which is the data that I showed you a few minutes ago. But what's also really interesting, if we look at the data for the antenna reactor, the wavelength dependence is completely different. And now it turns out that the plasmon controls the process, not the interband transition of the aluminum. So what's going on here? So the H2, so many of you might know a bit about palladium. Of course, it's a very well-known catalytic material, but also its interaction with hydrogen is very well known. Hydrogen dissociates spontaneously on a palladium surface. So what could be going on to make this H2 reaction so much more active on this antenna reactor? So it turns out that the hot electrons, as we excite the plasmon in the aluminum, the hot electrons can induce the desorption of the hydrogen atoms and kick them off. So we have now a stimulated desorption process of the hydrogen. Hydrogen is dissociated on the palladium, but the electrons within the palladium, which are driven by the electrons in the aluminum, okay, so they're coupled to each other, will induce desorption, and we form HD on the surface. So this is the first example of an antenna reactor that we began to study. So let me show you another reaction that's also very interesting for that same type of nanoparticle. So what we'd like to do here, we have exactly the same structure I showed you, aluminum palladium, and what we want to do is now a real chemical reaction. Let's take acetylene and let's hydrogenate acetylene using that structure. So acetylene is an interesting molecule in terms of how we hydrogenate it, because what we'd like to do is, if we hydrogenate acetylene, you'd basically like to make ethylene, but it turns out it's unavoidable. So ethylene is useful precursor for many sorts of polymers, many other fine chemicals. But if we add two hydrogen molecules to it, we'll make ethane, which is much less valuable. And it would be really great if we could be very specific and make only ethylene and not ethane. So we began to look at this as can we do this as a light-assisted process instead of just a thermal process? When this is done in industry and it's done just by purely thermally, it tends to be a pretty even balance between the ethylene and the ethane that's produced. So selectivity would be really, really great if we could achieve it. So let me show you here. So this is a contrast between taking that same aluminum palladium antenna reactor that I showed you and doing hydrogenation of acetylene. And if you look at the black points are the reaction in the dark. And they correspond to temperature, which is up on the top of the graph, right? So there's no light at all. We're just running the thermal reaction. And no matter what the thermal reaction, what the temperatures across this range, we find that we can't seem to, what we're looking at on the y-axis is the selectivity, or that ratio between ethylene and ethane. So the higher this number, the more selectivity we would have for ethylene. So if we look at the thermal reaction, we find that the ratio always, the best we can do is about 10 to 1. Right? But it tends to be relatively low. But look what happens when instead we do this as a light-driven reaction. Okay, so here we're applying the laser power density, which corresponds also to a temperature. So we always have some kind of temperature increase. We can't get away from that, but they always work together. So that's actually a good thing. So if we shine light, we find that on the photocatalytic process on an antenna reactor that we can go to very, very large ratios of ethylene to ethane. And so we have much more selectivity using this process as opposed to just a purely thermal process. And so we think this is an example of kinetic control where the hot electrons that are being produced in the antenna, that they're desorbing the ethylene after the addition of one hydrogen molecule, and before we have the additional hydrogenation that results in the ethane synthesis. So here's another example of doing a very simple reaction, but I'm doing it in a context that looks probably pretty bizarre to most chemists. So we can actually write this antenna reactor structure using methods like e-beam lithography. Actually use another type of method called a whole mask lithography, where we can write an antenna. In this case, we want to use one metal and then a catalytic reactor, which the reactive metal, right? So we have a plasmonic antenna here and a catalytic antenna here written on a planar substrate. And then we run a chemical reaction on this structure. And so the way this works, so this is a great illustration of sort of the mechanism of how this works, which is not as clear when I show the chemical catalyst as I show when it's very, very simplified structure. So the idea is very simple. We excite a plasmon in this antenna, okay? And the plasmon always has a little fringing field on the outside, which is due to the fact that we have this dipole moment. We have the electrons that go back and forth, so we form a dipole moment at optical frequencies due to the charge going outside of the to the electrons that are protruding beyond the ionic lattice of the metal at optical frequencies back and forth. So we have this field that extends beyond the nanoparticle itself. If the reactor is within that field, then that field on the antenna can also drive the electrons in the reactor. So normally these electrons, they don't even see light, they don't care. But the fact that they are within this fringing field means that they are also driven. And so it's these electrons, so they don't have to be connected even. They don't have to touch each other, these two metals, right? But the electric field, the electromagnetic field will drive these electrons. So it's kind of like a fake plasmon or a forced plasmon. And so the reaction happens here and the hot electrons happen here, right? But it's all because of the vicinity of the antenna, right? You take the antenna away and nothing's going to happen. You place the antenna there and it drives the field that then makes the reaction happen, but it happens on the reactor. So the hot carriers are generated in the catalytic reactor particle due to this coupling, what we can now think of as a forced plasmon or a forced oscillator. So we can see how this works. So my student Xiao Zhang made these structures, and you can see how beautiful they are. Made very, very large, but they were very precise dimers. This is what you can do with a method called whole mask lithography. So they're planar structures, right? So this is actually you can see the large area, but very, very precise dimers with different size gaps. And he could do the same. So we have, again, aluminum, palladium, but we're doing this in the most bizarre geometry that you could imagine. So we can do the same reaction, right? We know this reaction should work. Let's try to do the H2D2 reaction. And in fact, we can do this very nicely. But here we have some interesting bonuses. We can do this on a flat surface. Depending on how we polarize the light, we can actually control the chemical reaction with the light polarized in this direction versus the light polarized in the other direction, in the transverse direction. And what's also kind of what I think is also very, very exciting about this is because we've written the structure, we know exactly how many catalysts we've written on the structure. So we can actually quantify how much hydrogen is dissociated per laser pulse per catalyst, right? In a normal case of catalyst, you're not counting the number of catalytic sites. That's impossible. But here we now have a system where you actually can quantify absolutely every aspect of doing a chemical reaction. So we think this is a really exciting and special way to think about doing chemistry in now and in the future. So we also decided, so there was a question that had been plagued us, that had plagued us since our very first reaction. And you probably can figure out what it is. As I have said now several times, when you shine light on a metallic nanoparticle, on a plasmonic nanoparticle, on resonance, you heat it up. You are always going to have large thermal effects, but you're also going to have hot electron generation or hot carrier generation. So how can you distinguish the two from each other? Is there a way that you can definitively say, yes, we have hot electrons produced, or yes, we have only, or no, we have a purely photothermal reaction, when in fact, in many cases, you're going to have both. And so we decided to study a very simple chemical reaction that's very well studied. It's the decomposition of ammonia. And so it's very well studied by many people over many years. It's a very well-defined mechanism. And the rate limiting step is the associative desorption of N2. So once you have ammonia desorbed onto a surface, then you will be able, then you dissociate the hydrogen from the nitrogen, you leave the nitrogen on the surface, and then the barrier is related to the nitrogen recombining with each other and then desorbing from the surface. So that's our standard understanding of the mechanism of ammonia decomposition, which, by the way, is a very important reaction, and I'll mention why it is in a moment. So we then constructed an antenna reactor. This is a little bit different. It's basically copper. Copper is a plasmonic nanoparticle, it's a great optical antenna, and our active sites that we're using here are ruthenium. So ruthenium is a strong affinity for ammonia, for nitrogens, and so this was a very good reactor for combining as an antenna reactor in the structure. So with our copper ruthenium nanoparticle, you can see this works really well. If we look at how the decomposition works, this is actually very, very efficient reaction. We can see compared to copper, if I look here at photocatalysis, I have very, very strong photocatalytic response as opposed to the thermocatalytic response for the antenna reactor. Okay, so light on, light off, very huge difference. And you can see the reaction rate here. You can see the components, both the hydrogen and nitrogen and so on. And you can see comparing photocatalysis to thermocatalysis, this is a far more efficient process and here we're just measuring, of course, the hydrogen yield when we decompose the ammonia molecules. And so you see they're very different, and the mechanisms are quite different. So so what is happening in this? So what we're actually doing, as I'll show you in a moment, is we're actually changing. We've changed the reaction order, and we've actually changed the rate limiting step of the reaction. So a simple way to think about this is by cartoon. So if we think about the conventional way that ammonia is decomposed, okay, as I mentioned just a minute ago, it's limited by associative desorption. So you have ammonia sticking on the surface at all of the little ruthenium sites, and then it loses, we're breaking nitrogen-hydrogen bonds, but then we're left with nitrogen sitting on the surface, and it's just waiting, right? So the energy needed to drive the reaction has to do with desorbing these nitrogens and getting them to form N2 and leave the surface. So sort of like a poisoned catalyst is waiting. That's the rate limiting step. But it turns out that when we do the same reaction with light, we have a new mechanism. And I've alluded to this just a few minutes ago, that we actually can do desorption. So the electrons inside the metal, when you excite the plasmon, will desorb the actual adsorbates. So they lower the barrier to that particular desorption step. And so since they lower that energy, they keep the surface clean. And so we have more and more sites available for ammonia to now come on and adsorb onto the actual surface. So let's see what that looks like. If we look at the effect of carriers on reaction energetics, then we actually see here's the rate limiting step that we saw earlier. And then if we look at what happens for the light assisted process, we lower this barrier because now we are desorbing. So these species that are sitting on the surface, we're desorbing. So we lower this energy tremendously by using light instead of just thermal processes. So now we've actually changed the rate limiting step. The rate limiting step is now back over here. So this is no longer the limiting step for the reaction, but actually breaking nitrogen-hydrogen bonds, much lower energy is actually the rate limiting step for the reaction. So we're really changing the course of the reaction by introducing, by doing this out in an antenna reactor and by using a physical mechanism, which is the actual desorption of the associative species of the adsorbed species on the surface of the nanoparticle. That's great. It keeps the surface clean, right? This is one of the biggest problems with catalysts is that things react and then they sit there. And so so we've actually solved a big problem that's associated with a lot of thermocatalytic reactions. And we changed the reaction pathway. And now I'm going to show you a really beautiful but somewhat complicated plot. But I'm going to explain this to you so that you can appreciate this. So as I said, we lowered the reaction barrier. So if we look at the black lines here, all we're doing now, we're just measuring the reaction barrier to ammonia decomposition. These black lines show me what the reaction barrier is in the dark, right? So the slope of this barrier, the slope of this line gives me the reaction barrier. And then if I begin to shine light, I find that as I shine light, I change the slope of this line, right? As I'm lowering. So I'm measuring this at several different temperatures, right? I measure the reaction barrier to get the slope of the line. I do the same thing at different temperature, but I do it under illumination for several different temperatures. I try another wavelength and I do several different temperatures and I measure the barrier. I do another wavelength, et cetera, et cetera. And look, for each of these wavelengths, I change the slope of the line. So I'm changing the actual barrier to the reaction. And I find that at some wavelengths, I've changed the barrier a lot, some not so much. So I can actually map this out. I can, for example, I can take the wavelength that's the best, okay, 550 nanometers. I can go back, measure the reaction in the dark, and then I could turn on just the light of that wavelength and measure it as a function of intensity. And as I increase the intensity, at each intensity, I can measure the, again, I do the reaction at 4 different temperatures and I measure the reaction barrier. Okay, measure the reaction barrier, measure the reaction barrier. And so all this data now gives me the ability to plot out this really cool looking curve. So this axis here is the reaction in the dark. And then on one axis, I have intensity and the other one I have wavelength. So just as I show you in the very top part of this plot over here, that as I turn on the light, I lower the barrier. And especially at this wavelength here, this is the most effective wavelength, I lower the barrier a lot. I lower the barrier by almost a whole electron volt at this wavelength. And also I lower this as a function of intensity. So I map out this really beautiful contour that shows me the contribution of illumination, the effect of illumination on otherwise thermal activation barriers. So I can connect this new way of doing doing ammonia decomposition directly to the non-light assisted thermal mechanism for doing ammonia decomposition. Okay, so we can go to another reaction, and this is a reaction that's really important for industry, but it's also important for climate change. Many of you are familiar with this, I'm sure. So methane, CO2, of course, people want to remove CO2, but they really want to get rid of methane, because methane is about 25 times worse than CO2. And what this reaction does, this is called dry reforming. This is a way people are making what they call syngas, or in particular making hydrogen. Okay, hydrogen is great for hydrogen fuel, but it's costly to make hydrogen. And so we found that we can develop an antenna reactor that will actually make hydrogen. and will make hydrogen at much, much lower temperatures. It requires a lot of energy. We'll make hydrogen at much lower temperatures than industry typically uses. So I'm going to go into the details of the reaction, other than to say that a very similar catalyst to what I just showed you, copper ruthenium, is actually very, very useful for making hydrogen, and for making hydrogen out of methane, a gas we'd like to get rid of. And what's a bonus to this actually is if we space that the reactors on the antenna far enough apart, then we don't have a process called coking, which is where we have carbon-carbon polymerization, which will poison a catalyst. And so we find that when we have the right combination of ruthenium, that if it's sparse enough, you'll have a very good chemical reaction, but you will also have virtually no coking. So there's no lifetime associated with carbon contamination of the catalyst. And so there are also, this is more of the details of this reaction, which I'm not going to go into, but basically to tell you that that the actual energy efficiency of this reaction is quite extraordinary. It's a 15%, but also you have to realize this is at 15%, but this is also being done at a temperature that is much, much lower than what is normally done in industry, as I'll show you in just a moment. So, so in industry, if one does methane reforming, it's a little bit different reaction. You can do methane reforming a couple different ways. This is steam methane reforming, but in industry it requires 900 degrees, which means you have to do it in a big chemical plant. If you do this instead with light, you can do this at 200 degrees, which is a temperature you could actually achieve in your oven at home. Right? I'm not suggesting that you make hydrogen in your oven at home, but it shows you that you would need far less complex and expensive materials in order to actually make hydrogen. So I hope from this you see that this idea of using photons in clever ways, right, to lower reaction barriers gives us a new direction in terms of how we can think about doing catalysis in ways that will really save us a lot of energy. So we founded a company called Syzygy Plasmonics, and they are just doing incredibly well with developing this. What their angle is, as I told you, we do the nanoparticles, but what they did was they developed a chemical reactor that runs on light. And the key technology that makes this possible is solid state lighting. We can all appreciate solid state lighting as a revolution that's happened in the last 10 to 20 years. But this is, we don't think of solid state lighting sources. We think of them as lighting rooms, but we don't think of them as necessarily driving chemical reactions, but they're actually great for that, and they're super efficient. So this is a direction that's actually very, very exciting. So just to give you a quick introduction into the company side of things. So this is really just a different way of saying what I've been saying throughout my talk, but basically, chemistry has been done the same way for more than a century. That you use temperature and pressure, and you do run reactions at very, very high temperatures in large facilities, and then whatever you make at this large facility, you then transport this to the place where you want to use it. But if we can lower the temperatures, and also, of course, that also creates lots and lots of carbon emissions, and has a lot of cost, and having centralized production is not as efficient as if you could do this at low cost in a small facility, and you could do it right where you wanted to make the chemicals. So what Syzygy has been doing is developing this basic idea, light-based chemical reactor, and developing several different reactions that lower emissions and also lower cost, because we've lowered the chemistry. So we've lowered the temperature needed to do the same sort of chemistry. So their goal is to make a hydrogen production system. They're already well on their way to having their first demonstration model, which is going to happen earlier. It's going to happen this year, probably this spring or summer. And so this is something that's really exciting. So their goal is to make hydrogen fuel. Hydrogen fuel would be a great fuel to have especially for trucks and for heavy vehicles, but it's just too expensive. And so if they can lower hydrogen to the cost of fossil fuels, then there's a real tipping point. And so different aspects of the transportation industry that's looking very excitingly at hydrogen, like certainly cars. They're even talking about hydrogen. Airbus is making hydrogen airplanes now. And so the question is, how are you going to get your hydrogen and how cheap could it be? So, with that, I would like to conclude my talk and to just mention that the basic theme for us for plasmonics in chemistry is this idea of an antenna reactor concept. We can use a plasmon to drive chemical reactions where we have tailored the reactive sites on our optical antennas to do the specific chemical reaction. And we've gotten some insight now as we've done this on various different reactions for how precisely is the reaction barrier lowered by introducing light onto the surface of the catalyst, and how this basic idea could be commercialized in some interesting ways by lowering the temperature of chemical reactions. So with that, I want to also mention my collaborators for sure. My collaborators over the last several years have been the most brilliant people I've had the opportunity to work with. Emily Carter, who is now provost at UCLA, and her outstanding group members, Phil Christopher, who is just an amazingly creative and innovative chemical engineer at UC Santa Barbara, and Peter Nordlander at Rice, who is a theorist with whom we've collaborated for more than 20 years. And has a tremendous insight into surface science and into much of the physics behind what we've done. This is an old picture of mine. Several of these people have moved on to other jobs and have graduated, but they have played a huge role in this work. So with that, I want to thank you very much, and I'd be more than happy to answer questions.
Naomi, thanks so much.
Sorry, it went too long. I didn't realize.
No. We took a few minutes to introduce you, so you were fine. We have a bunch of questions that are all curated. And as I mentioned before, Rodrigo Noriega on the chemistry faculty at Utah and Carlos Baez at the chemistry faculty of UT Austin are going to take turns asking you the questions on behalf of the attendees. And attendees, you can keep typing in your questions in the chat, and the rest of us will get those into the window. So take it away. I think Rodrigo's going to go first, right, Rodrigo?
Yes, thank you, Christy, and thank you, Professor Halas, as well. So the first couple of questions come from Christopher Gonzalez, and the questions are, what happens if you make alloys of the transition metals and optical metals? And then is there a theoretical limit to the effect of illumination on activation barriers?
So those are great questions. The first question about alloying is an interesting one. From a simple point of view, from the antenna reactor that I showed you, you always want to be in a regime where the reactor itself is sparse, because you don't want the reactor to be affecting or degrading the plasmonic properties. So I know of some groups who tried to do this strategy early on, and they basically had too much, like they wanted to coat a plasmonic structure with a completely different reactive metal, and that would quench the plasmon. So you have to be in a regime where you still have the plasmonic properties and the strong optical optical field due to the plasmon that can then drive the reactor. So there's a sweet spot in that sense. And the second question.
The second question was regarding the theoretical limit on the effect of illumination on activation barriers.
That's a very good question. Can you? Well, what I've shown you is the case that you can lower a rate limiting step, but can you make the entire? No, that's. I mean, what we've been able to achieve is the lowering of rate limiting steps, but then we also have there are other rate limiting steps, right? So you know, I would say this. I would say it's a very clever question. I would say that I don't think anyone has really thought about whether there is an ultimate limit. so I don't have I can't say that I have a really good answer to that. It's a very, very compelling question, and thank you very much for that question.
Okay, the next question for you, Professor Halas, is from someone in the audience who asked that aluminum nanosynthesis is very delicate in compared to noble metals. So how can this be scaled to such stringent requirements? Having such requirements, how could this be scaled?
So that's a great question. I think that so to synthesize aluminum, you need very dry conditions. It's of course not done in aqueous solution. You need air, very well controlled atmospheric conditions. So basically, we do this either in a Schlenk line or more recently in a glove box. But that said, there's whole fields of chemistry that work exclusively under those conditions. So we're a little spoiled in the plasmonics world where we work with gold and silver, and we're very accustomed to aqueous chemistry. Those systems are great in aqueous phase. But if we then look at other fields in organic and inorganic, where there are many, many cases where people work in air sensitive environments, it's not that hard to achieve the standards that you need. They're just different. So just as reactions can, the scaling of reactions is always relative depending on what field you're in. I mean, obviously there's, in a lot of organic synthesis, they're never able to do, there's always kind of limited to batch scale processes. So I think that in that case, we're probably in a similar situation, that we're probably, at this point, unless people can really, develop high throughput methods, which is definitely doable. But certainly at the moment, certainly, batch scale methods, but they're not, I think the quote unquote bad reputation of aluminum nanoparticle chemistry has to do with the fact that people were really switching over from hydrophilic environments, and are not yet really really learned the basic protocols that you need to be practicing in order to be doing hydrophobic chemistry. But many chemists do hydrophobic chemistry. So that's how we learned. We basically learned by embedding within an inorganic chemistry group and learning the protocols that they use with triply distilled solvents, and how to keep things air free and so on. And so
I can confirm that's true, because I was the unfortunate physical chemist on that student's qualifying exam and had to listen to all that scary air-free chemistry.
Very good.
Thank you. The next question comes from Matthew Crane, who first thanks you for a wonderful talk. And then he's curious about the mechanism of hot electron transfer with heterostructures and the timescales involved. Do you think that hot carriers are generated in plasmonic materials and then transferred to catalysts where they participate in reactions, or does excitation of the heterojunction directly excite hot electrons in the catalyst?
I think that's a great question, and I think it really depends on the specific structure, right? So there are cases, and the reaction, right? So there certainly are cases where, so the simple examples that I showed today, we clearly we're clearly in a regime where we have coupling where the electrons, say for example, the electrons in the antenna are not transferred to the reactor. They're physically separated. So we see that that's not the case. So there are other cases, for example, one could also have as a reactor a semiconductor or a metal oxide nanoparticle where you have very long lifetime. So you could have, certainly you can have regimes where you have transfer of hot electrons into a reactive intermediate like a metal oxide, and then you have longer lifetimes, but you also have excited states, so there also could be mediated that way. But the basic mechanism of plasmonic excitation of a hot electron, into an orbital of an adsorbate would still, would still follow. So there's lots of different variations where one can see this. Can see this basic mechanism, variations of the mechanism.
Okay, the next question is also from Matthew Crane, and the question is, as a second question, I guess follow-up question, for industrial purposes, how does the cost and energy efficiency of photo excitation compare to the cost and energy efficiency of heating?
Well, it is much more efficient because you are. I mean, I don't have numbers in front of me, so I can't give you something that is, you know, I mean, this is, you know, sorry, I don't have, you know, specifics that I can necessarily share with you, but
It's not a chemistry question.
it's not, yeah, well, exactly. I would refer you to some other, to some other sources for.
You had the numbers for hydrogen, right? And you're at the very end of your talk.
But those are the ones you come prepared for, right? Like you're not a policy wonk. Like if she were, she'd be a lobbyist and not like a chemist.
Yes, I don't know specific efficiency numbers, so it's not off the top of you can. So one source that might be useful for you is our Nature Energy paper from 2020. I think we have some comparative numbers in that particular example, but that's not something where you can actually generalize. It's really specific to chemical reactions. But this idea that you can actually lower the temperature by hundreds of degrees by using photons in the right way is, that's a very general concept. And I think that also illustrates that it's not just a matter of how much energy you save. It's also a matter of, if I can do if I can run a reaction at 200 degrees Celsius, I can do it in a glass vessel, right? If I run it at 900 degrees, I can melt a glass vessel. Okay. So I have to have big steel things and lots of insulation and so on. So just manage the thermal management of something at very high temperatures is fundamentally different than something that is that is of course 100 degrees lower. So just those are basic general statements.
Thank you. Our next question comes from Tinji Song, and the question is whether regarding the stability of plasmonic particles during the catalytic reactions, especially after long-term usage, and how do you avoid the toxicity of the chemicals used to the plasmonic particles?
Well, very good. Very good question. So first of all, the stability, because we're in regimes where we are not at very, very high temperatures, right? So there's always issues about melting with certain metallic nanoparticles. We're staying in regimes below where we see irreversible processes. Okay. So if we see, I mentioned a little bit about catalyst poisoning by coking. So we found that in some regimes, the nanoparticles can be unstable. So we manipulate stoichiometry or manipulate some aspect of the nanoparticles to avoid that, right? We don't want them to be unstable. Sometimes we can do that, sometimes we can't do that, but we've had a couple, now several cases, some published and some to be published, where we have actually been able to manipulate the stoichiometry and we end up by controlling the stability. But we're always in a regime below melting. So the issue of nanoparticle toxicity is an interesting one, and it's also a somewhat humorous one. I'm not one to belittle toxicity. Toxicity is something we care deeply, deeply about. But one of the reasons why one would like to develop plasmonic catalysts is if you compare them with the other catalysts that might be available that are being used in other in conventional catalysis now. So for example, molecular catalysts, how do you remove the molecular catalysts? These are often toxic. So the whole issue of separation of catalysts is, from products, it becomes, an issue of environmental concern for all chemists, depending on what that reaction is. So, so in general, I don't think there's any issues of toxicity. I would say the issues of toxicity are related to these types of catalysts are certainly no more severe and much likely less severe than issues for conventional catalysts or other nanoparticles.
Thank you. The next question comes from Mike Berman. First, he thanks you for a wonderful talk. And the question is, are there different electron decay processes such as interband transition compared to plasmons?
Oh, absolutely. And there are also vibrationally assisted properties. There's also carrier multiplication processes where one hot electron can actually drive many lower energy processes. So there's a lot of interesting nonlinear processes that can be generated within the context of these chemical reactions. And we are actually looking at some of those in some of our current experiments. Thank you very much for that question. This is the tip of the iceberg. These are the baby steps. And so as we move into more and more different types of chemical reactions, we're beginning to see new and interesting phenomena that we hadn't realized were there. And I think that's very exciting. And that what's really helpful is working with theorists like Emily Carter, who's really been very, very helpful for understanding some of the energetics of multi-phonon processes that multi-vibrational processes that also play a role in these types of chemistries.
So we have a few more questions, but we don't want to hog up Professor Halas's entire afternoon, especially given what's going on there. There is a question that got asked. So before we kind of switch formats here, I think it's an interesting one given all the stuff that's been going on in the recent weeks with like GameStop and Reddit's stock market stuff. Is Chris Gonzalez desperately wants to know if Syzygy is publicly traded.
Oh, no, it's not publicly traded. It's an early stage company. They're very well funded. So
where can Chris get in on the ground floor of this is what he wants to know.
Really good question. I think this has a significant possibility of being disruptive, as you can imagine. There's real opportunities here for changing the energy landscape with this kind of approach. But they are early stage and they are not a publicly traded company yet.
And I think we probably have time for maybe one or two more questions before we switch formats for a little bit. The next question comes from David Misha. And the question is regarding how relevant are the lifetimes of electron hole pairs for reaction rates and yields?
Oh, great question. And this is something that's debated extensively. So I think that there are still, there are still arguments and controversies, and they will exist for at least the next 5 to 10 years about hot carrier lifetimes and how relevant they are for in different in controlling the efficiencies of different processes and controlling the efficiencies of tunneling into molecular orbitals, for example. I think that this is one of the reasons that I mentioned metal oxides earlier, because people will often say, well, semiconductors are far more, or you're going to have a much greater efficiency if you use a metal oxide as a reactor, because you will have a very long carrier lifetime associated with the excited state of a semiconductor relative to the hot electron in the metal. And yes, that can be true. So I think what we have to do is look, this field is in its early stages and it's exploratory. So we learn from each chemical reaction and each type of, we're not at the point where we can make really definitive statements about, no one's done the systematics of looking at many different types of, the same reaction with many different types of metal oxides, or the metal oxide and different types of adsorbate molecules, and what barriers are involved. So I think that those are really good questions, but at this point, and I hope the net effect of me being ambiguous on a lot of these questions is that people get really excited about this field and they want to work in it, because I think this is a field where a lot of people should be very eager to start to work, I hope. So I don't have, I don't have a really, there's no sort of general principle type of answer to that question, because the specifics of each chemical reaction and each photocatalyst are such that we can't make large general statements at this point. 5 years from now, perhaps yes. 10 years from now, yes.
Thank you. And the last question before we transition to the student and postdoc session is from Roy Auerbach, who asked, in the examples given of the island antennas, how important is the particle size for producing different plasmon resonances?
Very good question. It's I assume that he means the islands that are basically drawn as a planar device. So they're disks. So the size of the disk will control the plasmon, the resonant energy. So those were made in that structure was fabricated based on the earlier antenna reactor structures. And so we were basically going for using the same plasmon resonant energy. So we tuned the size of the disk to correspond to that same energy.
Thank you.
Okay, great. We do have some more questions, but those are student questions. And so now hopefully we can all take all of us together can take a moment to thank to Professor Halas for such a great talk and also answering tough and interesting questions. Thank you, Professor Halas. And then in addition, the other way to thank Professor Halas for all the faculty out there, please log off. Because now we're going to use the next 15 minutes that we have to let the students and postdocs have a little bit of chance to ask Professor Halas questions directly. And I know we held a couple of questions. I think it could be true that maybe Sean Meyer might be the first person. So if we'll just keep an eye here and give all the faculty a chance. Yep, people are logging off. And again, no way to know if it's everybody, but people tend to, and let the students go ahead and ask their questions. So Sean